In physics, we tend to try to prove physics laws. We don't generally discover new laws, but when we learn about laws, we try to prove them. And we always do this graphically. We try to graph relationships using the slope-intercept method and try to put something on, make the slope be some value that we know of that we're trying to look for. So if you remember, the slope-intercept form is y equals mx plus b. And if you have a graph, we can have a line on this graph that would maybe come up something like this. And make that line let's make that line a little smaller, a little too thick. So there we go. And in this case, the m, so we have the y is whatever we're putting on the y-axis. The x is whatever we're putting on the x-axis. And then m is the slope or the steepness of this line. The steeper it is, the bigger that number is going to be. The less steep, the smaller that number is going to be. And the b is the y-intercept. And that means where does this graph come across the y-axis, which would be right there. Now if and this would be a positive, that'd be a positive one right there. If we had a graph that kind of came down through this, then we still have a positive slope, but our y-intercept is a little further down here, right here. If we have a graph that comes right through the center, something like that, then the y-intercept goes through the 0, the origin, and so it's just 0. So that equation kind of simplifies to y equals mx. There is no y-intercept for something that goes down through the middle there. Now these are positive slopes, so m is going to be a positive number. If we had a graph going down this way, then that would be a negative slope. But generally we're trying to make it so that we have a positive slope on our graph that we're going to try to do. So we have certain mathematical laws and physics laws that we have equations for, and we try to rearrange them and stick them into this form, y equals mx plus b, so that we can figure out what we want to have show up. Like in Excel, we can have Excel graph this and then give us a slope, and that slope then should match some constant or some data that we have. So we'll look at an example here and see if you can follow along here. Let's take an equation that we've kind of looked at before in our deriving units. The Newton's universal law of gravitation, which is force equals a constant g times one mass times the other mass all over the distance squared between them. So these are two masses. This is how you can measure the force is between two objects. If you multiply this constant by both their masses and divide by the distance between them squared, you'll have force in newtons. So let's ask this question. What would I graph on the x-axis if I have a, I'm going to make a graph here. What would I put on the x-axis and what would I put on the y-axis so that when I get a line, or when I graph this, I end up getting a line that where the slope would actually be g. I want to figure out the number for g, and I want to graph something on the y and something on the x so that my slope ends up being g, or m slope equals the g constant. So what we need to always do is we rearrange this to make it fit into y equals mx and maybe plus b if there's a y-intercept, but in this case there's not a plus thing in here, so we're not going to have a y-intercept. We're just going to try to fit it into y equals mx only. Okay, so what we could do is we could multiply both sides by d squared. I'll have d squared times f equals big G times M1, M2. And if you look at this, even though it looks kind of ugly, it's in the proper form. We have this part here, which could be Y, and we have this part here, mass times mass, which could be X. And therefore G, this would be a straight line if we graph d squared F on the Y. So I'll put d squared F on the Y, and I'll take the product of my masses, and I'll put that graph on the X. Then the slope of this line is actually going to be G. So that's how we could do that. We could rearrange things here and then graph them, something on Y and something on X, so that the slope ends up being what we want it to be. All right, let's try another one here. Let's still go with the same thing. We have we'll still go with Newton's universal law. Let's do it again. G M1 M2 over d squared, and we get a graph here, which looked really bad. Sorry, as good as I can do it. There's X, there's Y. And I'm going to try to figure out what should I graph on the X and the Y so that I get a slope. Let's have the slope M be equal to d squared over big G M. So what would I do so that I can get a slope that's d squared over gm? So I need to rearrange this so that I have a d squared over gm. I could do f times d squared equals big G m1 m2. Let's make this m up here be like m2. I didn't say which one it would be. So then I could divide both sides by G and M2. So I'd have F d squared over G M2 equals M1, right? Okay, and if I rearrange that, I could do M1 equals d squared over GM2. I'll leave that right there, times F. And now if you look at it, we have something that correlates to Y equals MX. So what am I going to put on the Y-axis? I'm going to graph my mass 1. What am I going to put on the X-axis? I'm going to put force. And if I graph mass 1 versus force, I'm going to get a straight line, according to this equation, and the slope is going to be d squared over GM2. So that would work. I could do it that way. All right, let's do an easier one. You might remember that the equation for density equals, and we love density, right? We love density. Okay, density equals mass over volume. So what would I graph on the Y and what would I graph on the X so that my slope of my line is going to be the actual density. I want my slope to be density. And this one should be pretty easy because right now you can think of it, the slope-intercept form, another way we could write it is we're going to undo that. The slope, M, equals rise over run. Sometimes, it's called rise over run, which is y over x. So this is another way to write the slope-intercept form, and you'll notice the density equation is exactly in that form. So density would be slope if on the y-axis I put mass, and on the x-axis I put volume. And therefore I'll get a slope that will be the density. So that's a fairly easy one there. Let's do another one. Let's use this time the kinetic energy equation. I don't know if you remember that or not, but Ke equals 1/2 mv squared. And I want to know what would I graph on the y and what would I graph on the x. Here's my y and here's my x. And what would I graph on the y and the x if I need to get a slope of, let's see here. Let's get a slope. We'll put in a line there first. And let's say we want a slope that is equal to 2 over m. So what would we graph on the y and the x to get it, have Excel generate a slope that would be 2 over m to see if this law, this kinetic energy law, is correct. So I need to get 2 over m. So I could take 2 times the kinetic energy would equal mv squared. I could divide both sides by m. I'd get 2 ke over m equals v squared. And if I flip this over, I have v squared equals 2 over m times ke. And there it is, y equals mx. So on the y-axis, I could graph v squared. On the x-axis, I could graph kinetic energy. And when I do that, my slope will be 2 over m. And so I would have been able to prove that law. Look at one more that's really easy. One of our uniform acceleration equations. When you could go watch the derivation of acceleration equations, and you'd be able to see this. Is final velocity equals at plus vi. And so if I graphed final velocity on the y-axis, let's just do it this way. Let's say I graph final velocity on the y-axis, and I graph time on the x-axis. What would my slope be? And so when I get a straight line on here, I'll have something maybe like this. And so you'll notice that this equation is an awesome form already. Y equals mx plus b. We actually have a y-intercept this time. Pretty exciting. So that means if I graph vf on my y, which I did, and I graph time on my x, which I did, then my slope in the slope position should be acceleration, right? The acceleration constant. What is my constant acceleration? This is a uniform acceleration equation. So my acceleration should stay constant. That's what it is. The slope of this line would be acceleration. And my y-intercept is an initial velocity. So right here on the y-axis, I have an initial velocity that I would be going. So hopefully that makes sense. That's kind of what we always do in physics. We try to take different physics laws and rearrange them so we can put them into a y equal mx plus b format, and then we know what to graph on the y and what we should do on the x. So hope that helps you understand how do we graph relationships using the slope-intercept method.